In this video, we are going to have a few steps and tips to have an academic warm-up for doing a project or research in mathematics that could make just a learner or a curious learner to be a pattern seeker and then a rigorous researcher. Now, what is an academic warm-up? Now, an academic warm-up for research in mathematics means the process of absorbing deeply the definitions and theorems of your field and working through examples until patterns emerge, and then following those patterns all the way into original research. So you need to know the definitions, theorems, and examples, and then from them you learn a pattern and ask questions that and then find out the gap in the research what have been done already, and then you will have your own research. So the getting this pattern is actually the milestone in your research. Now, some of the areas in graph theory. So in this video, we are going to have mainly our focus is on graph theory. So as for graphs are concerned, the research areas, but not limited to what is mentioned here, spectral graph theory, domination theory, networks, matchings, algorithmic graph theory, energy of a graph, graph coloring, graph labeling. Now remember, for any of the areas in graph theory, you should be familiar with the definition of a graph and various classes and subclasses of graphs. Now what is a graph? A graph, G is this pair VE, where V stands for vertices and E stands for the set of edges connecting the vertices in V. An edge E, which is a pair of vertices. So from U to V, when you join by a line, then you call that to be an edge. So collection of edges is capital E, collection of vertices is your capital V, and G is vertices along with the edges. That is called a graph. Now vertices are represented by circles and edges are represented by line segments. The edges are used to connect vertices. An example of a 4-3 graph, that is 4 vertices and 3 edges. Suppose we have these 4 vertices, say A, B, C, D, and the edges, say the edge connecting A and B, A and C, and A and D. Then how will the graph, which is called 4-3 graph, would be? So you have A, you have B, you have C, and you have D, and you have the edges connecting A and B, A and C, A and D. So this is an example of a 4-3 graph. And the same way we have 4-6 graph. We have 4 vertices, namely 1, 2, 3, 4, and we have the edges from 1 to 2, 2 to 4, and here 1 to 3, then 2 to 3, and 1 to 4, 3 to 4. So we have 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2 to 4, and 3 to 4. So these are vertices, these are edges. So it's a 4-6 graph. And when we have a directed graph, we will have, if it is from 1 to 4, but not from 4 to 1 means, then we will have the arrow mark. But here, just a graph only we are mentioning. So that means we can classify graphs. So what are the major classes of graphs? So depending on the edge multiplicity, connectivity, and direction, we can have major classes of graphs as simple graph, multigraph, pseudograph, connected graph, disconnected graph, and here directed graph, undirected graph, and if edges carry numerical values, we have weighted graph. So these are some of the major classes of graphs. Now, if you want to know more information about different graph classes and the relationships, then you can visit this ISGCI website, which is a research database and software system. And this is an encyclopedia of graph classes that helps you to research what's known about particular graph classes. So this is the website for that. It will be mentioned in the description. Very useful website for those who are going to do research in graphs. Now there are many subclasses for general graphs, so we are going to list out some of them. Path graphs denoted as Pn, cycle graphs C suffix n, bipartite graphs, complete graphs, complete bipartite graphs, prism graphs, wheel graphs, fan graphs, book graphs, friendship graphs, star graphs, union of stars, bistars, double stars, Peterson graphs, generalized Peterson graphs, bull graphs, sunlet graphs, kite graphs, parachute graphs, gear graphs, web graphs, helms, flower graphs, corona, ladders, triangular ladders, duplicate graphs, triplicate graphs, caterpillars, twigs, trees with n internal vertices and more than n leaves, banana trees, pagoda graphs, Mongolian tent, and village, and etc. So a path graph. So now we'll just flip through all these graphs. We are not going to have any explanation for them. Just to know how the graphs would look like. So we are showing this cycle graph, bipartite graph, complete graph, complete bipartite, prism graphs. Like this, you make a same copy of the cycle and connect the corresponding vertices. And you have stacked or generalized prism graphs which look like this, and wheel graphs. To get a wheel graph, create a center vertex in a given cycle and connect this new vertex to all the other vertices. So that's your wheel graph. For different vertices you have wheel graphs. Fan graphs, you have fan graphs, book graphs, friendship graphs, Fn, star graphs, bull graph, sunlet and sunlet graphs, then kite graphs, parachute graphs, gear graphs. If we add exactly one vertex in each edge on the boundary of a wheel, we get gear graphs. So these are some of the gear graphs. Then web graphs. Make multiple copies of the cycle and connect corresponding vertices. Helm graphs. In a wheel, at each vertex of a cycle, if we add exactly one pendant vertex, we get helm graphs. So these are some of the helm graphs. Then ladder graphs. Add edges between corresponding vertices of two paths of equal length. You have them like this. So these are some of the ladder graphs. Triangular ladder. In a ladder graph, add edges between the corners. Then caterpillar graphs, banana tree, pagoda graph. In a ladder, add a new vertex at the top and connect this new vertex to the topmost vertices. So you have pagoda graph. Then from KNN to crown graph, how do we get? From K33, remove the corresponding edges. So these are some of the crown graphs. Now I already mentioned some of the areas in graph theory, all this. So in this now we are going to concentrate on graph labeling. So we are going to have on few slides on graph labeling. The concept of graph labeling was introduced by Rosa in 1967. A graph labeling is an assignment of integers to the vertices or edges or both, subject to certain conditions. So, types of graph labeling. Um, you have graceful labeling, harmonious labeling, magic labeling, anti-magic labeling, cordial labeling, then radio labeling, prime labeling, odd graceful labeling, total labeling, edge magic total labeling, and then vertex magic total labeling, super edge magic labeling, distance labeling, then LF2, 1, that labeling, and then geometric labeling, set labeling, integer additive set labeling, set indexer labeling, Fibonacci labeling, sum labeling. It continues. Difference labeling, product labeling, square labeling, mean labeling, super labeling, edge labeling, vertex labeling, again it's getting repeated, total graceful labeling, total magic, total anti-magic, and local anti-magic, modular, arithmetic, geometric mean, harmonic labelings, integer additive, difference cordial labeling, product cordial labeling, square difference labeling, edge odd graceful labeling, vertex odd labeling, edge sum labeling, lucky labeling, signed labeling, balanced labeling, and so on and on. So there are a lot of types of labeling, graph labeling that have emerged. Now most graph labeling papers follow this pattern. Labeling type plus graph class. So, for example, prime labeling. So, this is the type and which graph actually subclass caterpillar graphs. And then cordial labeling of banana trees. Odd graceful labeling of pagoda graphs. Then local anti-magic labeling of village graphs. So, many labeling papers they have come up by following this. That is, you have various graph classes and various labelings. So, suppose I have, say, I consider 20 graph classes, actually subclasses, and 20 labelings. Then we can have 400 possible research topics. So, that graph class caterpillar with too many labelings, and then banana tree, say, and then with that graph class you have 20 labelings. So like that, 20 into 20, so 400 possible research topics that you can have. Now, in as for labeling is concerned, these are the fundamental research questions that usually arise. Existence. Do caterpillar graphs admit prime labeling? See, we have got the list of graph classes, in fact subclasses, and we have the labeling type, prime labeling, and so on, harmonious, and so on. So the question is, can I combine those two? Right? Possibilities we have listed out, but whether we can have that existence, that must be questioned. So, do caterpillar graphs admit prime labeling? This, for example, that we are saying. And then, which caterpillars admit prime labeling? In we have various caterpillar graphs being listed out, and as for characterization is concerned, we must know whether which caterpillars admit prime labeling. Then construction. How do you construct that? So you have to provide labeling scheme, an algorithm, efficient method to label large graphs. Then maximum graph size with the property. What a property that we mentioned, which is the maximum graph size with that property, that extremal we call it as, and hardness of prime labeling. So that gives the complexity, and whether it can be extended to trees or forests. So that would be the generalization. So these fundamental research questions, as for labeling is concerned, even if you go for coloring also, then we have the fundamental research questions. So that would lead you to give you a lot of results. Now, many graph coloring papers follow the same pattern. You have graph class, that is subclasses, and coloring type. So, for example, acyclic coloring, star coloring, dominator coloring, equitable coloring. These are some of the coloring types. So, you associate that coloring type with the graph classes. Caterpillar graph, banana trees, ladder graphs, village graphs. So, a lot of graph class subclasses are available, and you have the coloring types also. So, combine them. So, that will give the coloring, I mean, the research as for coloring of graphs are concerned. So again, even in this case, you can have 20 graph classes and 20 type of colorings, so that you can have what 400 possible research topics. The existence and all we need to check whether we can combine this and that. So that is what is mentioned here. So suppose we study star coloring of ladder graphs. Then again, as said earlier, research questions would be, does every ladder graph admit star coloring, and characterization which ladder graphs have star chromatic number 3. Particular question that should arise, and whether is it possible or not. And then construction, give a method to color any ladder graph. Efficient coloring algorithm that must be given, and minimum star chromatic number. Hardness of star coloring that gives the complexity, that research question, and then extended to grid graphs. That is whether it can be extended further. So now a very powerful research formula is, you should know the compact research frameworks that are often used when studying graph coloring and graph labeling. These parameters act like control variables. Now, most papers in these areas study how these parameters behave on different graph classes. That is what we saw, isn't it? So, almost all papers can be generated by graph class plus coloring or labeling type plus that research question. So, you will get, based on the various research questions, you will have lot of results. So you have graph subclass, caterpillar, banana, ladder, type. Example only we have given: prime labeling, cardinal labeling, star coloring, existence, construction, extremal value. So these are the questions. Just we have summarized and given them here. Now the following are all studied using exactly the same research framework: graph energy. Based on, so once you have the graph, you can get the matrices corresponding to the graph, and then once you have the matrices, you can talk about the eigenvalues of the matrices, and then the energy is based on the eigenvalues. So graph energy, metric dimension, burning number, coloring, labeling, even pebbling. So all those are emerging topics. So you can use the somewhat similar research framework to do research on these topics too. Now, most modern graph theory research follows the pattern graph class, graph parameter plus research question. This is what we already said, where the parameter could be coloring or labeling parameter, domination parameter, energy parameter, metric parameter, spreading parameter. That is your burning number. So again, this is the combination what we have been telling. So just the summary of them. That's what is given here. Because we added one more, so because of that, again, a summary. And for any graph invariant, the research pipeline is, so you must define the parameter. What is that parameter that you are going to consider? Whether your entire thesis is going to be on pebbling or burning number or your labeling or coloring. So you must know which parameter that you are going to follow. So define the parameter. Then compute it for small graphs. We have got lot of graph subclasses. So compute it for smaller one. and study special graph classes, then find bounds, develop algorithms, pose open problems. Only then on the research you will have, because otherwise, if you want to be yours to be unique, then open problems you must find that only when you have the entire research thing, then you will know that where you find the pattern and what is the difficulty that you found. So that could be posed as open problem, because it may be true for certain cases, it may not be true for certain other cases. So in that case it becomes an open problem. So that you have. And then how usually researchers generate problems? See, by just listening to the previous slides, now that you would have known that this is how the new problems that we can generate for doing research. So here, anyhow, we will list it out. Your known concept plus new constraint. Domination is known concept, then you impose certain conditions so that you will arrive at Roman domination. And you know that concept of domination, and you impose some other condition, you will have rainbow domination. Then graph parameter 1 plus graph parameter 2. See, so far we have been saying that you have graph classes, that is subclasses, and then graph parameter. Then the research question needs to be asked, and then you will have the results. But now here it is, nowadays it is the trend, graph parameter 1 plus graph parameter 2. That two parameters you can combine so that you will get hybrid parameter. So that is domination, you have one parameter, coloring another parameter, so that you have dom coloring. And dom coloring for various graph classes you can discuss. And burning number and vertex coloring. So chromatic burning you can have. And graph parameter plus a structural constraint plus study on special graphs. So these special graphs are the algebraic graphs. They are also emerging very well. Zero divisor graph, unit graph, total graphs, and so on. They are based on the algebraic systems. That is, you may have groups or rings or vector spaces. So there you have the elements satisfying certain axioms, and you call them as, say for example, zero divisors, two elements that you consider A and B in a ring, and if you have the product to be zero, then you call them, but both of them are non-zero, but yet the product is zero. So in that case you get zero divisor graph, annihilator graph, and so on. So you can have the structural constraint, you have weighted weight regarding weight, and graph parameter pebbling, and special graph, zero divisor graph. So like this you can have. And just check when you define. See, the very difficult part is finding the combination. Like if you consider graph parameter 1 and graph parameter 2, that you are getting hybrid parameter, and it should I mean you should get results for at least some of the graph classes. If nothing can happen, then that combination cannot be considered. So a lot of opportunities are there, but what we need is only patience. So if you are using that ISGCI research database and software system, if you are using that, then all this that you can see from that website, you choose a graph class, say for example caterpillar graphs. Then you like to know what is its superclass. So it is ISGCI, not IFGCI. So it will result in trees, outer planar graphs, chordal graphs. So check known algorithmic results. So like domination, number, coloring, Hamiltonian path. Find what is not known. So your example research question could be, what is the DOM chromatic number of caterpillar graphs or any other subclass? So this can become a new research problem. So, and if you have, see, if you have a certain path to be contained in certain trees and so on, then what is true for trees will be true for path. So, like that, the superclass in ISGCI you can find, and then you can easily conclude some of the results. They can be mentioned as corollaries for the main theorem or result that you are going to quote. So, for that, this website will be very useful. So, finally, in every graph lies a hidden structure waiting to be discovered. May your research reveal many such beautiful structures. May this be a pleasant warm up to your exploration of graph theory. Wishing you joy and discovery and success in your thesis completion. Thank you.